So what I want to do today is do first a couple problems related to numerical integration that we haven't done before, but I've given on exams before. So you should pay attention. And then a couple more problems related to improper integrals. And you'll have another probably relatively small assignment due on Friday, and then a longer one due next Monday. So this first problem is of a type I've often given on exams before, where we only have data, no formula for your function that you're integrating. So this problem, number 25 here, use this table to estimate the total distance traveled from time 0 to time 6 using left, right, and trap. Okay, so we've got time data, no units given. You could imagine it to be seconds. You've got velocity data, no units given. You could imagine it to be meters per second. Since these velocities are all positive, you could also think of this as a speed. There's no function name given, but you certainly can give it a name if you like. You could call this f of t. How many intervals do we have here? 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. That's 6 intervals. In fact, A equals 0, B equals 6. And you can see that delta t, the change in time over each subinterval here, is 1. So n must be 6. There must be 6 subintervals. So when it says compute left, right, and trap, we're really computing left of 6, right of 6, and trap of 6. We've got 6 subintervals, 6 rectangles for the first couple, at least, that we were finding the area of, and then with the trapezoid rule, again, we are averaging them. We really can't do, at least with delta t equal to 1, the midpoint rule or Simpson's rule, because we don't have more data. We don't know the values of the function at, for example, 0.5 or 1.5 or 2.5, which we would need if we were going to use the midpoint rule, at least with delta t equal to 1. You might find it helpful to draw a picture, but you don't have to. Think about it conceptually. With the left-hand rule for each interval, and the first interval here again is 0 to 1, you take the left endpoint to find out the height of the rectangle given by the function value, in this case 3. So 3 is the height of the first rectangle in the left-hand rule, and its base is 1. In fact, the base of every rectangle here is going to be 1, so we're going to be multiplying by 1 each time, which means I don't really need to write it, but for extra emphasis, I will. For the second interval, 1 to 2, the left endpoint is 1. Function value, height of the rectangle is 4. So you get 4 times 1. For the third interval, 2 to 3, the left endpoint is 2. Function value, the speed, is 5. You need 6 terms in the sum because there's going to be 6 rectangles. And that means for the left-hand rule, you're not going to use the last data value. You're not going to use the function value at the right endpoint. B equals 6 in this case. This is representing the areas of 6 rectangles altogether. Again, multiplying by 1, it's not necessary to write, but I'm doing it for emphasis. 3 plus 4 is 7, then we get up to 12, then 16, add on another 15, you're going to have 31 for the left-hand sum. If the units for t were seconds and v is meters per second, this would be in meters. If t was in hours and v was in miles per hour, this would be miles. For the right-hand sum, for each interval, you take the right endpoint. So the first interval again here is 0 to 1. The right endpoint is 1. Function value is 4. 4 times 1 is the first term. That's the area of the first rectangle. For the second interval, the right endpoint is 2. Function value is 5. Take 5 times 1. In fact, pretty quickly you see you get the exact same numbers except for the very first one that we got before, except we also add on the last one, 11 times 1. And that's going to give you 39. The left-hand rule seems to be probably too small. The right-hand rule probably too big. If we average them, that should most likely give a better approximation. The trapezoid rule does that. 31 plus 39 divided by 2. 70 divided by 2 is 35, halfway between 31 and 39. Is it a guarantee that the trapezoid rule is the best? Actually, not necessarily. I mean, in most circumstances, your function is going to be pretty well behaved, increasing slowly, then decreasing slowly, then increasing fast. But it's possible, in theory, between these values of t that you see here, that the function is doing wild things up and down, okay, for all you know. That hardly ever happens with most real life situations, except for data about earthquakes, shaking, right? There you have oscillations that go up and down really fast as one example. But even on a small enough time scale, even earthquake oscillations would be relatively smooth. So most likely it's not doing anything weird. So most likely the trapezoid rule is the best. Most likely the left-hand rule is too small and the right-hand rule is too big. Though not an absolute guarantee, because we don't have a formula and we don't have the actual graph. Okay. So again, you can't do the Simpson's rule or midpoint rule with this unless you changed delta t to be 2, for example. Let's also go over problem 39 that you had for your homework. And on Friday's assignment, I'm going to assign number 40, a similar problem. This table that you see right here, is that big enough? Zoom in here. Gives approximations to an integral whose exact value, true value, actual value is 7.621372. Does the integrand function, they don't put the word function in there, but it's assumed you know integrand means the function you're integrating. And you can tell from the context, appear to be increasing or decreasing, concave up or concave down. That's where these pictures that we drew on Monday are relevant, and they are in the book. Page 400. We'll think about the trapezoid and midpoint rule because those are a little harder. Left and right are, well, let's look at quick at this picture. Left and right are a little easier. When your function is decreasing, the left-hand rule gives you rectangles that are both the darker ones and the lighter ones put together. Put those rectangles together to get bigger rectangles, and you can see the left-hand rule is giving you areas that are too big when the function is decreasing. The right-hand rule are just the darker ones. Those are going to be too small when the functions are decreasing. It reverses when the function is increasing. Left-hand rule is too small, right-hand rule is too big. You can see this function appears to be increasing. The left-hand rule is too small, the right-hand rule is too big. Not a guarantee, but that's what it appears to be. That's why they phrase it the way that they do. With the trapezoid midpoint rule, when the graph is concave down, what the trapezoid rule does is it essentially draws a trapezoid and finds the area of that trapezoid where the top of the trapezoid is a secant line to the curve, meaning it connects 2 points in the curve, not a tangent line, secant line. And if the graph's concave down, that line is going to be underneath the curve, so the area is going to be too small. On the other hand, when the graph's concave up, the secant line is above the curve, and the area of that trapezoid is too big. It's a little trickier with the midpoint rule. So here's your typical situation with the midpoint rule when the graph is concave down. You got your subinterval, you've got your midpoint. Go up to the graph at that midpoint. The midpoint rule is a sum of areas of rectangles. However, if you take the top of that rectangle right there and rotate it around its midpoint until it becomes a tangent line, the new trapezoid has an area bigger than the area under the curve because the tangent line is above the curve. And that trapezoid has the same area as the original rectangle because we were rotating that line around the midpoint. It doesn't change the area. Hope that makes intuitive sense. The area of this shaded triangle equals the area of that shaded triangle. Meaning the area of the trapezoid shaped like this is the same as the area of the rectangle shaped like this. Top of the rectangle is right there, top of the trapezoid is right there. It's the tangent line there, not the secant line. Over here, the tangent line, okay, when it's concave down is above the curve. When it's concave up, it's below the curve. So the midpoint rule is too big when the graph is concave down and too small when it's concave up. It's too big when it's concave down. It's too small when it's concave up. That number is a bit too big, right? There's the true value. Must be concave down. This function appears to be increasing in concave down. As far as the error goes, remember that error is always actual value minus approximate value. And again, that's nice because that goes in alphabetical order. That's the way I remember it. So with the first line here, the left-hand rule, the error when n is 3, take the actual value, 7.621372, and subtract the approximation, 5.416101. That'll be a positive error because the approximation is too small. The difference is going to be positive. There, I've got it, 2.205271. And with the right-hand rule, 7.621372 minus 9.307921 is going to be negative. It's a negative error. I won't write it down, but here it is on the calculator. 7.61372 minus 9.307921 ends up being negative 1.686549. Negative error. That's just keeping track of the fact that the approximation is actually too big. Again, this seems a little counterintuitive. When the approximation is too small, it's a positive error. When the approximation is too big, that's a negative error. We do want to keep track of it that way. That is, I think, the best way to do it for some reasons I won't go into. For the next column, you needed to use the principle we talked about on Monday, that when you increase n by a certain factor, like in this case, n goes from 3 to 30, so it's increasing by a factor of 10. For the left and right-hand rules, that means the errors go down by a factor of 10. So the error for n equals 30 with the left-hand rule, you just take this number and move the decimal place one spot to the left to get 0.2205. Do the same for this one for the right-hand rule. Move it to the left one spot to get negative 0.16865. It's a little different, remember, for the trapezoid midpoint rules. Their errors, when you increase n by a factor of 10, would go down by a factor of 10 squared, 100. So you should have moved the decimal point to the left 2 spots. And with Simpson's rule, it's even better. When n increases by a factor of 10, the error goes down by a factor of 10 to the 4th, 10,000. Move the decimal point to the left 4 spots. These things are rules of thumb. They're rough approximations. They're not exactly correct. But that's what you should have done for the problem. So I'll give you a similar problem, number 40, for Friday's assignment. I have put problems like this on exams before as well. Can I clarify anything? These facts about what happens to the error as n increases are in the book, though they're stated a little differently than what I stated them. On page 402, it says for the left or right rules, each extra digit of accuracy, meaning error goes down by a factor of 10, requires about 10 times the work. n increases by a factor of 10, like from 3 to 30. For the trapezoid midpoint rules, each extra 2 digits of accuracy, meaning the error goes down by a factor of 10 squared, 100, requires about 10 times the work if n increases by a factor of 10. The error goes down by about a factor of 10 squared. And finally, for Simpson's rule, it says each extra 4 digits of accuracy, the error goes down by a factor of 10 to the 4th, requires about 10 times the work. If n increases by a factor of 10 from 3 to 30, you could expect the error to approximately go down by a factor of 10 to the 4th, meaning move the decimal place to the left 4 spots. And that, again, is all emphasizing Simpson's rule does the best.